Hello and welcome back to my differential geometry series. I'm going to be talking today about orientations and top forms. So we last time saw that there is a vector space which you can construct over another vector space called the exterior power. So kth exterior power. And it's a subset of the tensor algebra over V. And so tensors of rank K over V. And I'm going to use this now to construct something useful, because up until now you haven't seen any applications of this construction. So let's talk about orientations. An orientation is a choice of ordered basis for V. So suppose that you have two bases. That was not a real English letter. Suppose you have two bases, so B and C. So you set two bases, and then you compute the change of basis matrix between them. So we say that, okay, so this is the change of basis matrix. The change of basis matrix. So if the determinant of P is less than 0, we say that B and C determine the opposite orientation. For V. So let's say that if the determinant of PCB is greater than 0, then B and C determine the same orientation. So what this means is that if you have a choice of coordinates, I'll call it like this, and you set x hat and y hat and z hat in your coordinate system, so I'm using R3 as an example here, then this basis would be x hat, y hat, z hat, for example, and we could, in principle, construct some kind of a right-hand rule so that our thumb points up along the z-axis and our fingers curl from x hat to y hat. So what would happen if you exchanged x hat and y hat? You'd end up with y hat here and x hat here and z hat here. So this is y hat, x hat, z hat now. So this basis, this choice of coordinates, now has exchanged a right-hand rule for a left-hand rule. You now curl your fingers towards y hat from x hat again, but if you do that, you're curling them in a clockwise manner instead of a counterclockwise manner from above. So this is what orientation means intuitively. If you were to compute the or the change of basis matrix, so P, B, C, I'll call this one B and this one C, then what it would be is 1, 0, 0, 0, 0, 1, 0, 1, 0. And this thing indeed has determinant -1, as you can compute. So determinant of BPC is -1. So this is sort of the idea behind an orientation. Another way to compute orientations is to set x hat and y hat and z hat to have a dual basis, which I'll call, I'll just call it x, y, and z for now, or x tilde, y tilde, and z tilde, so that we can now compute x tilde, wedge y tilde, wedge z tilde. And I'm going to call this thing omega. So this object is an element of lambda 3 of R3. And if we were to compute the change of basis on this form, then what would happen is, if we did omega and we computed it in the other basis, you would end up with, well, y hat, or y tilde, wedge x tilde, wedge z tilde. But we saw that if you were to exchange two covectors in the wedge product, y tilde, wedge x tilde is negative x tilde, wedge y tilde. So this thing becomes negative x tilde, wedge y tilde, wedge z tilde. So this is how we sort of look at change of orientations. So if we have the dimension of a vector space is n, and we have omega in lambda n, so the highest possible lambda of v star, then omega determines an orientation on v, because a change of basis by a transformation P, B, C simply multiplies omega by a constant. So if you work it out, you end up with PCB. If you act this on omega, so how will I note this? Of omega, then, and this is going to be written in the C basis, then you get some constant times omega written in the C basis, essentially. And that K is the determinant of P from B to C, or from C to B. So I can work out the detailed change of basis for you, rule for you now. If you have a dual basis, so E1 En, a basis for V star, then a form alpha in lambda k of V star gets transformed under a change of basis by you simply apply the change of basis to each of the component forms. So what you're going to do is E1 wedge dot 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 wedge P C of En or Ek times the coefficients. And of course there's going to be some combinations of these things, but that's okay. Yeah, so what you do is you just apply this inwards. And because alpha depends on the position, alpha of, oh, actually no, it doesn't right now, so we can ignore that. We will get there in differential forms, but for now alpha is not a function, it's just a constant. If alpha were a function of the position in the vector space, we would have to edit it a little bit, and we'll see that later. So for top forms, so n forms on V with dim V equals n, alpha gets transformed to the determinant of the transformation times alpha. So this is called the determinant formula. Yeah, and in fact this gives us a nice way to compute determinants of arbitrary transformations, because what you can do is just transform a top vector, or a top form, and then you get the determinant right away as a prefactor. And you recognize the top form out front, and you can just cross these off and you get the determinant. So it's pretty nice. And of course this ties the determinant to the wedge product. You've probably seen the formula for the determinant in terms of -1 to the k times the determinant of the n by n minors of k, and then you sum over that. So this -1 here is really because of the wedge product formula. So this is here for the same reason. There are minus signs in the wedge product. It's because if you were to exchange two columns of the matrix, you should introduce a minus sign. Same with in a wedge product, if you exchange two of the vectors or the covectors in the wedge product, you get a minus sign. So VW gets, so determinant of VW is negative the determinant of WV, and similarly V wedge W is negative W wedge V. So these two go hand in hand. Great. So that's all I had to talk about for orientations on vector spaces, except for the fact that there are two unique classes of orientations. I suppose I should do that as well. So let V equal Rn, then the orientation of Rn in a given basis is plus or minus 1, I'm going to say, times x hat wedge y hat wedge dot 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 in order. And I'm going to choose these vectors outright just to be any vectors I like, and then relative to this orientation I can construct other orientations. And so there are going to be two classes of orientations. So one class is going to be O plus, and it's the set of all orientations. So it's the set of all alpha in lambda n of Rn star, such that alpha in the standard basis, which is this one, is equal to positive x hat wedge dot 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 wedge xn hat with some constant that is in the positive real numbers. And similarly for O minus, you have alpha in lambda n of Rn star, such that the representation of this form in the S basis is negative k x1 dot 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 wedge xn, where k is now a negative real number. So these two classes, O plus and O minus, if you union them, you just get lambda n of Rn star. So they are a disjoint partition of the top forms. So we call these equivalence classes. Because any two orientations in this class are equivalent. I should probably give these some nice double striking so that you don't just see them as a 0 or something. Yeah, they're a letter O, capital. So they're equivalence classes of orientations. And these two equivalence classes determine opposite orientations. Great. So that's all there was for orientations, and thanks for watching.